Hello, Djordje Romanic here. Welcome to Fundamentals of Weather and Climate playlist. Consider an air parcel like so. And now we add amount of heat to this air parcel, delta capital Q. Then the first law of thermodynamics tells us that this amount of heat, delta Q, that enters the air parcel will be used to increase internal energy for the amount delta U and to do work in the amount delta capital W. Let us say this in even simpler terms. This amount of heat that entered air parcel will be used, first term, to increase temperature of the air parcel. So temperature will go up, and to do work. Here we have to be even more precise. To do work means that the air parcel can do work against the environment or do work on the environment. And in simpler terms, it means this air parcel can expand for some amount of its volume. Now you might say, what happens if we remove heat in the amount delta Q? If we remove heat from this air parcel in the amount of delta Q, this equation still holds. It tells us that in that case, temperature of the air parcel will decrease and the environment will do work on it. In other words, the air parcel will shrink. That's the first law of thermodynamics. These two terms on the right hand side can be expanded, so we can write that delta Q is equal. Internal energy is mass of the air parcel times CV, which is specific heat at constant volume. That's the amount of heat we need to supply to this parcel of air to increase temperature for 1 degree Celsius or 1 Kelvin while keeping volume V constant, and times change of temperature delta T. This is the internal energy. And work is pressure P times change of volume delta V, capital V, and that's this change of volume I indicated here. Now, as I discussed in some of my previous videos, in atmospheric sciences we don't like to do with masses because it's difficult to define mass of a fluid, whether it is air or water, so we tend to divide this by mass m, and then delta capital Q divided by m is small delta Q is equal, this mass will cancel over here, CV delta T plus P delta V divided by m. But you know that V divided by m is equal 1 over rho, density, because density is mass divided by volume V. And this 1 over rho in atmospheric sciences, so we don't have to write 1 over rho, we write alpha. So this over here, therefore, is simply delta alpha. And this is first law of thermodynamics per unit mass when the internal energy and work terms are expanded. However, I would also like to tell you that this is not the form of the first law of thermodynamics that we typically use in atmospheric sciences. Question, why? Answer. Because, you see, this term has change of, this is called specific volume or change of density, 1 over rho. And we don't have instruments readily available that are measuring density or change of density. So in this form, it is difficult to apply this law to the air outside or inside, doesn't matter. However, there is a way around. There is the so-called Mayer's formula, which says that R, gas constant, that I introduced in my video on the gas equation, equation of state for an ideal gas, is equal Cp minus Cv, where Cp is specific heat at constant pressure, the amount of heat we need to provide to an air parcel to change its temperature for 1 degree Celsius or Kelvin while keeping the pressure, not volume, pressure constant. Substituting this here, an equation of state that I introduced in previous videos, it can be demonstrated that this delta Q can be rewritten as Cp, not Cv, Cp delta T, not plus but minus, and these are reversed, alpha delta P. And this is the form of the first law of thermodynamics used in atmospheric sciences. Because now we have change of pressure rather than change of specific volume or 1 over density, and this is much more easy to measure in atmospheric sciences. We have available instruments to measure change of temperature and change of pressure, so we can use this law to carry out calculations. You might say, yes, but you still have alpha, which is 1 over rho. Yes, but this alpha can easily be replaced using equation of state for an ideal gas, and in that video I exactly told you that the purpose of that law is often to replace alpha and density in other equations. Okay? All right. So let us now discuss a little bit this law and how we can interpret it. I will erase this and then get back to this equation. Here is our first law of thermodynamics, and let us examine it. Option A, we add or remove the amount of heat delta Q from an air parcel, but we do it in a way that there is no change of pressure. So that means, as you can see, that delta Q, the heat added, will exclusively go to increase temperature of this air parcel. This process is known as isobaric. Isobaric means no change of pressure. Are there purely 100% isobaric processes in the atmosphere? No. It's approximation. But in fact, there are many processes that are very nearly isobaric. Examples. Pretty much all radiation processes are isobaric. Absorption of solar radiation by an air parcel is very nearly isobaric. Emission of long-wave radiation by an air parcel that we discussed earlier in this playlist is nearly isobaric process. If we have a large-scale advection of warm or cold air, which I also discussed earlier, then that process close to the surface is often quite close to being isobaric. Microphysics processes that we will study later, condensation, evaporation at small scales in the clouds, are nearly isobaric. Turbulent mixing in the atmosphere is nearly isobaric process. So you see, there are many processes that are, to very good approximation, almost isobaric. Now, using the same framework, we can examine option B. And you can see that option B is if we add or remove the amount of heat delta Q from an air parcel, but we now force temperature to stay constant. Delta T equals 0. Then our first law of thermodynamics is equal delta Q is minus alpha delta P. This process is known as isothermal. Are there any purely isothermal processes in the atmosphere where the amount of heat is not used to change temperature but to do work? The answer is no. And in fact, it is very difficult to find even nearly isothermal processes. You see, I gave you, 5, 6 examples of nearly isobaric processes. But it is difficult to cook up examples for even nearly isothermal processes. One example let me think. Well, one example that I will give you is isothermal in the following way. It is isothermal because there is equilibrium between other processes that are making it isothermal. Let me tell you what I mean. Here is the Earth's surface. So this is height Z. And we studied in chapter 2 of this playlist that during night, Earth is losing energy through radiative cooling. So the Earth is radiating energy in the long wave spectrum, and then this air ends up being warmer than the surface. And air ends up being warmer than the surface, so that means the air will now heat the surface through conduction and conduction mostly. So the air is cooling because surface is cooling. Surface is cooling, gets cold, air is warmer, and then air starts warming the surface. Now, in principle, nothing here, as you can see, is isothermal. Temperatures are changing. But at some point, temperature of the air will drop sufficiently so that partial pressure of water vapor in the air is equal saturation pressure of water vapor, and we will get these green particles that over here I use to indicate fog. This is how radiative fog forms. Now, when fog forms, that means we have condensation. Condensation, as we studied, releases latent heat of condensation. Now, look at this. Surface is losing energy through long wave radiation. Air is supplying heat to the surface, but also heat is supplied to the air through latent release of heat. So at the end of the day, temperature of this air over here is nearly constant. And that's nearly isothermal process. You see, I cooked it up, so it's a consequence of other processes. Loss of heat through warming the surface is compensated by the gain of heat from phase change of water vapor into the liquid water and associated latent heat of condensation. That's almost isothermal process. Is there any other example of isothermal process? For example, phase changes are isothermal processes, because if we have boiling and then we increase temperature, it will be the temperature of water does not increase until all water evaporated. Or if we have melting of ice, the temperature of the ice and the surrounding water will always be 0 degrees until all ice melted, and then the temperature of liquid water starts increasing. So phase changes are isothermal processes. Okay, that's enough, because it's very difficult to, find isothermal processes in the atmosphere. And lastly, C, you remember that the first law of thermodynamics could also have been written by change of alpha, and alpha also appears here. So are there any processes where delta alpha is 0, where there is no change of volume? These processes are called isovolumetric, I think. There is another name for them, but I forgot. Isovolumetric is good enough. Are there any isovolumetric processes where we add or remove heat, but the volume stays the same? Almost none. Almost none. The only one I can think of would be some process where heat is added or removed so rapidly that the parcel of air, so to speak, doesn't have time to adjust its volume. And one example that crosses my mind is during lightning, that we will study later. You have lightning channel that is plasma that is very, very hot air. It can reach temperature of 40 degrees Celsius. And before that hot plasma starts expanding and we hear thunder, that's what we hear, sudden change of, sudden expansion that causes very strong pressure perturbations, and we hear it as sound wave. Well, before that expansion, heat is absorbed, but there was no change of volume. That would be nearly or almost perfectly isovolumetric process. But other than that, there are really no other examples I can give you that I can think of in the atmosphere. Okay. So this was discussion of the first law of thermodynamics. It is one of the fundamental laws in physics and therefore in atmospheric physics and atmospheric sciences as well. We will use this law extensively in our next videos to study the so-called adiabatic processes. And then finally, what is an adiabatic process? Because I just introduced it. ABCD, adiabatic process, is the process where delta Q is equal 0. You see, we studied all these different cases where when we add or remove heat and something happens with the right hand side. But what about if we do not add or remove any heat? Then that is called adiabatic process. And you can see in the case of adiabatic process, we have that Cp delta T is equal alpha delta P. You might say, but this is boring. What can happen if you do not add or remove any heat? You will see in the very next lecture that many things can happen, because you still have interplay between these two terms on the right hand side. Temperature can change, but that has to be associated with the change of pressure. And we will study adiabatic compression and expansion of an air parcel when the process is adiabatic. So that means processes A to C are not adiabatic. And how do we call them? We call these processes diabatic. And this is adiabatic. Now lastly, I gave you so many examples of many processes. Are there, of all these processes, can I cook up any example of adiabatic process? The answer is yes. There is no perfect adiabatic process. Just there was no perfect isobaric, isothermal, and isovolumetric process. There is no perfect adiabatic process, but there are processes that are very nearly adiabatic. For example, if we have a parcel of air that is moving around, adiabatic process means there is no exchange of heat between this parcel of air and the environment, and that's very good approximation over short time scales, minutes, seconds, hours even, because the amount of radiation that would be absorbed, let's say solar radiation, is negligible, or the amount of radiation that this air parcel emits are almost equal to 0. So the processes associated with everyday motion of air in many situations are nearly adiabatic. But the next video will go into great details of adiabatic expansion and compression, so there is no need to dwell much more here about that. Lastly, I would like to say there is also a second law of thermodynamics, which I'm not going to have entire video in this fundamental playlist, but I would like to tell you here that the second law of thermodynamics tells us if you supply heat to a system, you can never actually have perfectly isothermal process. In other words, you will always have some split between heat going into doing work and heat going into increasing temperature. And the second law of thermodynamics tells you what is the maximum amount of work a system, that's usually called engine in the term of second law of thermodynamics, what is the maximum amount of work, efficiency of a system for a given amount of heat. In other words, there is no 100% efficient system or 100% efficient engine. You know that from everyday experience. If you have a vacuum cleaner, example, then that vacuum cleaner takes energy, electrical energy, and it will do work. It will suck dust and dirt from your floor. But at the same time, it will also get warm. Amount of heat or energy is not just used to do work, but also to increase temperature. If you are running, you supply energy to your muscles. Muscles are doing work, but eventually your body also gets warm. And the second law of thermodynamics tells us you can never supply energy and just do 100% work. Something will always go into increasing internal energy, or in simple words, temperature. Thank you for watching. Please make sure to like and subscribe. Let me know how you are enjoying this playlist. And until next video, goodbye.